propellers. Yay, propellers. Oh, wrong slide. What is the reason for having propellers on board the aircraft? So you can push, or if you stick it in the back of the airplane, you can pull, or if you stick it in the back of the airplane, you can push the propeller around. How does it do that? It does it by changing rotating energy or kinetic energy from the engine into thrust. What do you make propellers out of? Well, you can make them out of wood. Problem is, if you hit some gravel, then the wood kind of gets chewed up. So generally speaking, you're going to see a leading edge made out of metal, like brass, on a propeller. Here you can see the tip, and the leading edge has some metal on it, so it doesn't wear out so fast. Steel alloys, typically found on older and or bigger aircraft. There's a really old airplane from the 50s, and these blades are made out of steel. They're nice and polished and oiled, so that's why they're shiny. They're not aluminum. And of course, aluminum alloy is very popular on smaller aircraft, like on a 172. In this case, it's a Mooney. This is unpainted aluminum right here, and that's what you got on a 172 with Seminole, stuff like that. And then composite, or stuff glued together, Kevlar, graphite, fiberglass. Here's a C-130J, and it has composite propeller blades on it, and you can get a little more funky with the shapes made out of composite than made with metal. Fixed pitch props, like we got on our 172. Climb prop, standard prop, cruise prop. Usually comes out of the factory with a standard prop. Effectively, a climb prop is the same as being in low gear in a car. So you can rev the engine up. You don't go very fast, but you can go up a nice steep hill. Cruise prop, on the other hand, is about the same as being in high gear. You can't speed up very fast when you're slow, but boy, you can go really fast at the top end without overspeeding the engine. And a standard prop is like being in a medium gear. So if you want climb performance, and or you want the engine to rev up so you can get all of its horsepower out of it, like if you're at a high altitude, you would want to put a climb prop on it. If you didn't need climb so bad, or you were at a low pressure altitude, like you flew out of sea level all the time, but you wanted to go fast, true air speeds, then you'd put a higher pitch propeller on it versus a low pitch propeller on it. Low pitch is like being in low gear, so you can let the engine rev up. High pitch is like being in high gear. And on fixed pitch propellers, for instance, 1969 Cessna 172 came out of the factory with a 75-53 prop on it. 75 is the diameter, and the 53 is the pitch. There we go. It's not, the 53 is not the angle of the propeller, but how much it would if you spun the propeller around all the way around once. If you spun the propeller around all the way around once and it came back around, it would travel forward. If it was in a solid medium, say, well, not solid, but like Jello, it would move forward 53 inches. So on fixed pitch props, if you're looking at the pitch, it's talking about how far the propeller would move forward if you rotated it one revolution, but it didn't have any slippage. I believe we have mostly, if not all, climb props on our fixed pitch props at Embry-Riddle Prescott. However, constant speed props are a lot more complicated when it comes to operating them, so we're going to spend the vast majority of our time on them. If you have low pitch, you'd be, say, at 3 degrees. Here's the propeller, and here's the engine shaft, so here's the axis of rotation. And 3 degrees would be typical low pitch. So what that would mean is that if this was at exactly a 90-degree angle to the axis of rotation, and let's try a different color. Here we go. Let's try blue. And we put a propeller blade so that this right here was 3 degrees. That would be low pitch. That is, it doesn't cut much air for each revolution. 17 degrees would be something more like one that's already drawn. And if we took this and looked at this angle right here, if this was 17 degrees, that's going to be high pitch. So on a constant speed propeller, typically we're going to have it vary between plus 3 degrees all the way up to plus 17 degrees of pitch, and therefore on takeoff the blade can be at a low pitch. Like in low gear we can accelerate, and as we go faster and faster and faster, and to keep the engine from going too fast, we can let the propeller blade will be pushed towards a higher pitch, so the engine RPM stays constant. That's really what it means. It's talking about engine RPM being held constant by having a variable pitch propeller. "85 degrees, that's feather. And you're only going to find feathering, or let me rephrase that, the vast majority of the time you're only going to find feathering on airplanes that are multi-engine. Again, we take this plane of rotation of the propeller, and this angle right here, if that's 85 degrees, that equals feather. And you'll go, well, Mr. Johnson, if we rotated it to 90 degrees, we get less drag, and you got a good point. But if we leave it off just a little tiny bit, and I'm over-exaggerating it, that way when the wind hits it, it'll push the blade back towards lower pitch when we're trying to unfeather it. And the difference in drag between 85 degrees and 90 is extremely small. So we're going to get low drag when we feather the propeller. But if we only feather it to 85%, it's a little bit easier to start the engine back up if we needed to. And then minus 15, I love minus 15. That's reverse pitch. You're only going to find reverse pitch on turbine-powered airplanes with propellers, and reverse pitch is really just extra low. So if here's the plane of rotation of the propeller, and this blade right here keeps going lower and lower and lower, this is coming up here, we get all the way down to 3 degrees. That's normal low pitch. But on turbine-powered aircraft, you need to take AS311 if you want more details, is reverse pitches. It actually goes down all the way to 0, and the blade is actually negative. So here we actually have negative 15 degrees, but the propeller is still coming down here, so it's actually going to blow air forward or blow air in the reverse direction, hence the term reverse pitch. But reverse pitch is just really, really extra low. The blade goes to 0 and then goes beyond 0 all the way up to minus 15. So actually, minus 15 would be full reverse, because it'll only go that far. There's a lot of forces acting on propellers, including centrifugal force pulling the blades out, and alcohol, tobacco, and no, that's not what ATF is. ATF is aerodynamic twisting force. Aerodynamic twisting force, ATF. And here I got a really nice picture. Aerodynamic twisting force. You got to understand that with a propeller, we're rotating it about wherever it's bolted into the propeller. If you stick your hand out the window of a car going fast enough and you increase the pitch of your hand, it'll tend to increase even more. Since we're rotating around the middle, and the center of pressure of asymmetric airfoil subsonic is ahead of the center of the blade, or the head of the center of the airfoil, it's going to tend to push the blade to a higher pitch. So ATF pushes the blades towards higher pitch. However, centrifugal twisting force, that's what CTF stands for. CTF stands for centrifugal twisting force. CTF. If you don't have any counterweights on the blades, like this one right here, this would be, you don't usually see it because the spinner's covering it up, but a Cessna 182, the Super Decathlons that we fly, these are all, I don't know what model the Super Decathlon is. These are all single-engine airplanes. The vast majority of single-engine airplanes have blades, and they don't have any weights bolted onto them. I'll show you a picture here shortly. They just have plain blades. You know what? I think if I show you something, it'll help a lot. Let's try it like this. let's have somebody standing around, and they got a string with a rock on it, and they start spinning it around and around and around. Let's say his fingers and feet and toes, and they have a lot of donuts, and they need a haircut. Whoops, I'm getting distracted here. Okay, they spin it around and around and around. This rock is slowly going to go up to, get close to the plane of rotation. The axis is going to be right here. And so the faster you spin it, the farther it's going to go up. Centrifugal twisting force tries to bring all of the mass into the plane of rotation. So remember that. Centrifugal twisting force tries to bring all of the mass into the plane of rotation. So now, here's another airplane without counterweights, an airplane propeller. I know there's a picture. Here we go. If this is the axis of rotation right here, just like that person spinning, and this is right here, this is the plane of rotation. Then as we spin this propeller round and round and round, centrifugal twisting force is going to try to bring the mass of the trailing edge and the mass of the leading edge into that plane of rotation, which equals lower pitch. So if you don't have any counterweights, without counterweights, it's going to take the blades towards a lower pitch. And airplanes without counterweights, that's the vast majority of single engine airplanes. If you took the spinner off, you'd find no counterweights. Just like these. However, if you do have counterweights with counterweights, and that's all multi-engine propellers, if you do have counterweights, now it's a different story. Check this out. So if we have an airplane with counterweights, I'll show you another picture here. Here's an airplane. Here's the blade. The blade's running like this, and there's a counterweight sticking out of it at 90-degree angle. Here's the blade, and here's a counterweight sticking out towards you at 90 degrees to the blade. And here's another one. Here's the blade at 90-degree angle to that. Here's this big old honking counterweight. So these are all multi-engine propeller blades. So here I have, sticking it up again, just like that person standing along. Here's the axis of rotation, and here is the plane of rotation. And here's our blade, and at a 90-degree angle to the blade, we got a big ol' honking counterweight. So we've got this big counterweight. Well, if we spin it around and around along the plane of rotation, this weight is a long way away from the place where it rotates. So centrifugal twisting force acting on the counterweights is going to tend to pull it down into the plane of rotation. Problem is then, this pitch right here, the blade pitch, is going to get higher. So that's opposite to what it'll do to a blade that has no counterweight. Centrifugal twisting force acting on the counterweights is going to give you higher blade pitch. So you have to know, does my propeller have counterweights? If so, centrifugal twisting force will try to take the blades towards a higher pitch, and if you don't have counterweight, centrifugal twisting force will try to take the blades to a lower pitch, and you're going, oh geez, Mr. Johnson, that sounds so complicated. Oh, I forgot to tell you, ATF is always less than CTF. So it's always going to counteract it. So I'm not even going to worry about ATF, because we're either going to have CTF with counterweights making the blades go to lower pitch, or if we have CTF on an airplane with engine propeller with counterweights, that's going to make the blades go towards higher pitch, just from the blades spinning around. Now, if we have a multi-engine airplane that has counterweights, it's also going to have a feathering spring. So here's the same thing turned sideways. Now, there's literally going to be a piston inside of here. And in a multi-engine airplane with counterweights, in a multi-engine airplane with counterweights, we're going to pump oil, and I'll get to that here soon. We're going to pump oil from the governor to this side of this piston. Now, this piston is connected to the blades. So when the piston moves back and forth, it's going to make the blades go to higher and lower pitch. The centrifugal twisting force acting on the counterweights is going to make the blades go to higher pitch. Also, inside of here is going to be a feathering spring, or more than one feathering spring, and it's going to be pushing down on this pitch actuator. This is really just a hydraulic actuator. We're just going to use engine oil boosted up to 200 or 300 psi by the governor, but it's really just a hydraulic system. These feathering springs push this piston down, and that pushes the blades towards higher pitch. So the feathering springs take the blades towards higher pitch. Let's say it's hooked on over to this side. There we go. So if it rotates right here, if this piston goes down, it's going to push this that way. The nose of the blade is going to come up to a higher pitch. And then there's a third thing on some airplanes. A compressed gas charge. There's a Schrader valve right here. That's just an air pressure valve, just like on your tires on your car or an airplane or a bicycle. Here, if you push on the top, you can hear the air coming out. Listen, when I push on it. The compressed gas charge in here, we'll give it another color, make it really cool. Yeah, let's try orange. This compressed gas charge in here, it's also pushing the piston, the pitch actuator, to go to higher pitch. So this compressed gas charge, I've never seen it on a turboprop, and there are some multi-engine airplanes that don't have it, but it's very common to have this compressed gas charge. So on multi-engine airplanes that have counterweights, there are three things that take the blades towards higher pitch. Centrifugal twisting force acting on the counterweights, feathering springs pushing on the pitch actuator to make the blades go to higher pitch, and compressed gas charge pushing on the pitch actuator to make the blades go to a higher pitch. And on these multi-engine airplanes with counterweights, there's only one thing that makes them go to a lower pitch, and that's governor boosted oil pressure. That's this oil coming from the engine that is then kicked up to a higher PSI from the governor, and we'll talk some more about the governor later. And it's pushing this piston in the opposite direction of the feathering spring, in the opposite direction of the hot compressed gas charge, and it will push the piston up, pull on the blade, and the blade will go to a lower pitch. So all you have to do on a multi-engine airplane that has counterweights is to either let these three forces do their job and let the governor oil out, or if you want the blades to go to a lower pitch, you have the governor pump oil in and fill this up, this hydraulic actuator, and push it over in one direction. Essentially, we have a single acting actuator. That is, we're only using hydraulic pressure on one side to move it in one direction, and we're using something else to move it in the opposite direction. God, that was a great slide. I love that part. Hey, compressed gas charge. So here we are, multi-engine with counterweights, higher pitch, and well, I'll get to this here shortly. We'll get to it. Yeah, we already showed it. And governor boosted oil pressure is multi-engine with counterweights goes to lower pitch. Now, here's a single engine airplane, piston, propeller. There's no counterweights up here. So centrifugal twisting force, CTF, on blades with no, CTF with no counterweights. That takes the blades to lower pitch. So what we're going to do, we're going to have, I need a different color here. Let's try this blue here. There's a piston in here, a pitch actuator. But now what we're going to do is through this tube, we're going to pump the oil to the upside. We're going to fill the governor boosted oil pressure in here. We're going to pump it to the other side of this pitch actuator, and it's going to push the pitch actuator in the opposite direction. And of course, it's connected to the blades. So this governor boosted oil pressure is going to make the blades go in the opposite direction, higher pitch. So it's exact opposite. And remember, this airplane with no counterweights, these blades with no counterweights, that's generally single engine props. If you took the spinner off, you'd see no counterweights on the propellers. So for single engine props with no counterweights, centrifugal twisting force acting on just the blade, not acting on the counterweights, takes the blades to lower pitch, and governor boosted oil pressure takes it to higher pitch. Ta-da! I already showed you that stuff. Oh. So there we go. You need to know this stuff right here for multi-engine with counterweights, and this one right here, and this one right here for single engine with no counterweights. I don't need that anymore. And I'll tell you more about the governor in a little while. Oh, I did want to show you this about the governor. Here's the inside of a governor. See this thing right here? This is a pump. It's an oil pump, and it kicks up the pressure from the engine. The engine oil pressure is going to come in, I don't know, it's going to come in here somewhere, and it's going to come in here somewhere around, say, 50 psi. But that 50 psi is not enough pressure. Remember, force equals area times pressure. 50 psi is not enough pressure to have enough force to move the propeller around. So we're going to kick that pressure up. We're going to pull it in at 50 psi, and we're going to be able to pump it out to the propeller at 200 to 300 psi, which is why I keep calling it one more time here, governor boosted oil pressure, because it's not just engine oil pressure, it's noticeably higher than that. Okay, what's the purpose of a propeller blade? To produce thrust. I know this stuff's really hard. Pitch actuator, that's that cylinder, that's that piston inside of the blade hub, or inside of the propeller dome. That's what changes blade pitch. And of course I already showed you that part in two different kinds of engines, two different kinds of propellers. The propeller control lever, that's what's inside of the cockpit that you as the pilot get to operate. Be careful, that propeller control lever is just telling the governor what speed you want. When you push forward, it says, hey, make the engine go faster RPM. When you pull it back, you're saying, hey, make the engine go to a slower RPM. It then decides what it needs to do to the blade pitch to make the engine go faster or slower. And the propeller lever is usually blue, and it's usually the one in the middle. So we got the throttle, the prop control lever, and then the mixture, and this would be on a single engine airplane. Of course, the governor, what's the purpose? It's there to control engine RPM. I know these ones are really tough. Here's the governor. It's bolted on the side of this engine, and you're going to have a connection in here, and you're going to make this arm go back and forth, and you're going to be squeezing down on the speeder spring. I'll get to that before we're done. And it's going to allow oil to go out, and this is where the propeller would be bolted on. It's either going to allow oil to go to the propeller, or it's going to let this oil come back out and drain to the bottom of the engine. That's really all the governor can do. Well, I guess it could shut it off and keep whatever oil is in there. So it can either pump oil to the propeller, it can let the oil drain out and go back to the engine, or it can keep whatever oil is in there and not let any in or not let any out. I'll get some more about that here soon. Okay, the purpose of an unfeathering accumulator. An unfeathering accumulator is literally exactly the same as a hydraulic accumulator. Hey, wait, it is an accumulator. Except instead of being round, unfeathering accumulators are usually a cylinder. And they've got fluid on one side and a compressed gas charge on the other with a little Schrader valve. See if you push it, can you hear the air coming out? Oh, now I got to put some more gas in there. And it's just going to store energy. And it does it by storing a volume of oil at high pressure. Oh, wow. Volume and pressure. Sounds like hydraulic energy to me. Dun, dun, dun. I'll talk to you some more about hydraulic unfeathering accumulators here shortly. The accumulator is hooked into the governor under normal operation. Under normal operation, in addition to the governor pumping oil to the propeller, the governor, remember, here's the oil pump. Here's our governor oil pump inside the governor. It's going to pull in the oil from the engine and kick it up to 200 to 300 psi, and it's going to fill, it's going to charge this up. So it's going to push this piston against the air. So now we'll end up having 200 to 300 psi gas charge, and we'll also have 200 to 300 psi oil pressure in here. So it's going to be storing this engine oil at a pressure and have a volume of it, so it's just sitting there doing nothing. The vast majority of the time it doesn't do anything. When we unfeather the engine, what we can do is we can actually release this oil through the governor and go to the propeller, even if the governor isn't spinning, so we can get the propeller to go to low pitch. And I'll talk to you some more about that here before we're done. Gear reduction. Gear reduction allows the engine to spin fast and develop a lot of horsepower, but keeps the propeller spinning slow so the blades don't come up on Mach and have a lot of blade tip drag. And here is a crankshaft coming in from an engine, and here's a gear right here, and here's a big old gear right here. So as this one rotates around, this one won't rotate all the way around, so the propeller is going to be bolted on right here. So this may have a 2 to 3 reduction gearing, so that when the engine spins around 3 times, the propeller only spins around twice, so the propeller spins slower. Again, that allows the engine to spin fast and develop a lot of power, but keeps the propeller spinning slow. Of course, downside is you got to overhaul your engine more often. A propeller synchronizer. A propeller synchronizer keeps all the engines spinning at the same speed. I got a little diagram here. If you flip the switch, what it does, there'll be a master governor, and you'll set the RPM for both engines really close, and you flip the switch on, and what that does is there's a box, and it's measuring RPMs from both engines, and what it does, it tells this actuator to push or pull on the governor of the opposite engine, and it makes it change until both engines are spinning at exactly the same RPM. It makes less noise, there's less vibration. If you've ever been in a twin-engine airplane and you hear it going, you try to change the prop lever so it goes, and it's not quite so irritating or quite so bothering or noisy. And the synchronizer does that for you. And training airplanes typically don't have synchronizers because it's one more thing to maintain. A synchro phaser keeps all the engines running at the same RPM, and it makes all the propellers stay in phase. Excuse me, and this reduces the noise even more. Here's a really great picture of an airplane that not only has the synchronizer turned on, but has the synchro phaser turned on. You'll notice this C-130, just so you know, this is United States Marine Corps. Fat Albert is, they fly around the Blue Angels equipment and ground crew personnel. You'll notice that all of these propellers are at the exact same rotation. Not only are they spinning the same RPM, which is what a synchronizer does, but a synchro phaser, in addition to keeping the RPMs the same, it'll have, just one master, and then it'll make all the other engines, it'll actually get the blades to be just in the exact right position, so they're all rotating together, and this reduces the noise and reduces the vibration even more than just a synchronizer. That's a pretty sweet plane. Okay, how do constant speed propellers work? It's kind of funny you call them constant speed propellers, but it's really the propellers keeping the engine at a constant speed, and the propeller is varying pitch, so it's a variable pitch propeller. The governor is really just a mechanical computer. The governor gets two inputs. One of them is from the propeller control lever, that is from the pilot. You push it forward saying, hey, I want higher RPM, or you pull it back saying, hey, I want lower RPM. And the second input the governor gets, hopefully I have a picture here, is from the engine. This shaft coming in from the engine to spin these the governor oil pump. This shaft comes up and it spins these weights around, these fly weights. And these fly weights are operated by centrifugal force. They get flung outward and they pull the shaft up and down, and it's hard to see, but this either allows oil to go to the propeller, allows oil to come back from the propeller and drain back into the engine, or it moves it just right and it doesn't let any oil in or out. And that's based on the RPM of this shaft, and the shaft is spun by the engine. So these two direct inputs, one is engine RPM and the other is propeller control lever position. You're actually telling what RPM you want the governor to set. And here's the three things it can do. The three outputs is you can either pump oil to the engine, you can let the oil come back and drain out, or correction, this is to the propeller, or let the oil out, or if the RPM is exactly what you're asking for, it doesn't send any oil to the propeller and it doesn't let any oil out. On speed condition is the speed where the RPM you're asking for is the RPM that the engine is spinning at. The fly weights are perfectly straight up, and this shaft going up or down, opening, closing passages, or essentially it's a valve, it's closed. Essentially this is a three-way valve. Let oil to the prop, let oil out of the prop back to the engine, or don't let any oil in or out. Those are the three things that the governor can do. Another way to describe it would be to say that the governor has three output options: higher RPM, lower RPM, or maintain RPM. And these are either going to be oil to the prop, oil out of the prop, or keep oil in the way it is. So, and depending on whether it's with or without counterweights, sending oil to the prop or sending oil out of the prop is going to make the RPM go up or make the RPM go down. So you really got three things: pump oil to the propeller, let the oil out of the propeller, or keep what's in there, and that'll maintain RPM. And of course, little governor operation, we're going to keep the engine at a constant speed by changing the blade pitch. And of course, I'll show you a picture here. Little speeder spring, little flyweights. Here's a different picture. The speeder spring, when you're moving the propeller control lever, you're actually pushing down on the speeder spring, and that makes the flyweights come in. So now the governor thinks you're spinning too slow, so it's either going to pump oil to the propeller or let oil out, so it'll speed up. As this shaft, which goes down here to the engine, speeds up, the flyweights will come back out, and then the governor will shut off and won't pump oil to or let oil out of the propeller, and then it's on speed. So I like it here because we have this nice oil pump. We can also see the speeder spring, and that's all you're doing when you move the propeller control lever, is you're pushing down or letting up on the speeder spring, saying you want more RPM or you want less RPM, and then the flyweights. If they're straight up and down, that's on speed. If they're in or out, it's either underspeed or overspeed, depending on whether it's with counterweights or without counterweights. So, what are you asking for when you're moving the prop lever? You're asking for a change in engine RPM. The governor is going to decide what blade pitch is needed. And of course, where does the oil come from to supply it from? From the engine. It's using engine oil all this time. Okay, you're in a multi-engine airplane. If one engine quits, you want to be able to feather the engines. To feather the bad engine, get the propeller facing into the wind so it doesn't have too much drag, so hopefully you can still keep flying. So if you here's a blade in feather, you can see the wind coming across it, not too much drag. You can see the wind coming across it, not too much drag. So that's the feathered position. That's 85 degrees of pitch, plus 85 degrees of pitch. That's the feathered position. One could say that the feathered position is really very, very high pitch. I say that because if you've got a propeller, here we'll say there's the propeller blade, and here's the plane of rotation, and you're already at 17 degrees of pitch. That's high pitch. To get to feather, all you're doing is allowing the propeller to go to even higher and higher pitch until it's at about 85 degrees, and that's just very, very high pitch. Just like negative on reverse pitch is very, very low pitch. In this case, feather is very, very high pitch. So what does it take to take the blades to feather? Well, hopefully I have a picture. Yay! Well, let's see. We got our pitch actuator, and it's hooked up to the blade, and we got our counterweights here. So we got three things taking the blades towards high pitch, or possibly we got centrifugal twisting force acting on the counterweights. It's trying to go in and take the blade toward high pitch. The feathering spring, it's pushing down on the pitch actuator, trying to push the blades towards higher pitch. And then, of course, some airplanes have the compressed gas charge inside of here. All these gases in here pushing down. Did I make the right sound? Pushing down. That's trying to make the pitch actuator go, push down, and make the blades go to high pitch. So there's just that one thing taking the blades towards low pitch, and that's governor boosted oil pressure. So really all we have to do to get this blade to feather is to drain the oil pressure out. So if you pull that prop lever all the way back, or in some airplanes it's a separate switch or lever, you pull it back so that it allows, instead of pumping oil to the pitch actuator to counteract these three forces, we let the oil drain back to the engine. Then these three forces will all take over. Why? Because they all take the blades towards higher pitch, and in fact they'll take the blades all the way to feather. Unfeathering. There's two ways to unfeather. First of all, the reason I said maybe is you might have an unfeathering accumulator, and depending on the airplane you can move a lever, or on our PA-44s you push the prop lever forward. It was all the way back when you feathered it. You push it forward and that opens a valve. Tell me I got a picture. Oh, I don't have a picture, darn it. That opens a valve and allows the unfeathering accumulator, that governor boosted oil pressure in here at 200 to 300, to go through the governor, because you've got that lever in the cockpit, you've got that prop control lever. It's telling the governor, and it'll allow that fluid to go to the pitch actuator, and it'll push against the pitch actuator, against those three forces, and take the blades towards lower pitch. So all you're doing is using the unfeathering accumulator to supply pressure. Even though the engine's not spinning, the governor's not spinning, the governor does not have the oil pump rotating. But if you can let the oil from the accumulator, which was sitting there for a few minutes while you messed around with the airplane, you can have it push against that pitch actuator and push against those three things, those three forces. It'll push the blades towards low pitch. As if the airflow is coming along and the blade starts going towards lower pitch, it'll hit the blade and start making it rotate. And if you've got the fuel on correctly and got the ignition on correctly, the engine will start up. Yay! And you didn't even have to use the starter motor. However, if you don't have an unfeathering accumulator, that second way is you have to crank the starter motor. Now, to crank the starter motor, remember the governor's on the side of the engine here, and in the back of the engine is the engine oil pump. So down here somewhere you got the starter motor, and it's starting the crankshaft. The crankshaft spins the oil pump. The oil has to pump oil to the governor. The governor has to spin, and then oil will start going to the propeller. Well, the pressure in here is going to have to build up to 200 to 300 psi, and it's not going to do that until we get a lot of oil from the engine oil, and the engine oil isn't going to pull engine from the reservoir up until the starter motor is spinning the crankshaft. So you might have to crank the starter motor 20 or 30 seconds, and that's a long time, to get the engine up to enough speed to pump enough oil to the governor, so the governor will, and the governor is spinning off of the crankshaft too. It has to spin enough to get the oil pressure high enough to push the blades back to low pitch so that the air can catch it, and the propeller will start spinning around and around and around. And the bad news is, if you keep cranking the starter for a long time, it's going to wear out the starter. So typically, you're going to find unfeathering accumulators on training aircraft. Oops, can't spell training. Because you're going to be feathering and unfeathering it a lot. Mostly on bigger aircraft that aren't being used for training, they don't waste their time and weight and cost on unfeathering accumulators, because you're really only going to feather the airplane engine if it really fails, and if it really fails, you're not going to try to unfeather it. Okay, feathering spring or latches here. You're going to find latches on airplanes that on multi-engine airplanes with counterweights. You got to remember, if we've got this pitch actuator here, and governor boosted, oil pressure is pushing it to go to low pitch, because this thing is connected to the propeller. So if this goes forward, the blade's going to go to lower pitch. If this governor stops spinning, when you shut the engine down, the governor's going to stop pumping oil out here. So the feathering spring is going to push, the compressed gas charge is going to push, and if the engine's rotating a little bit, the centrifugal twisting force acting on the counterweights are going to tend to take the blades towards high pitch. And in fact, it may take it all the way to feather, which is really just really, really high pitch. The problem is now, if the propeller blade is in the feather position right here, when we go to start the engine up, the propeller is going to have a whole lot of drag. So we'd really like the propeller blade to stay in low pitch when we shut the engine off and stay there. So low pitch, here's the plane of rotation. Low pitch is lower than this. Low pitch is only 3 degrees. So if we've got our propeller here in low pitch, what we'd really like it to do is stay in low pitch. So let's say that the propeller is pointing down right now, and in it is a metal pin inside of the propeller, and there's a spring on it pushing the pin inward, and inside the propeller hub there is a nice spot for this. Now this spring in here has a calibrated strength, so that below an idle RPM, not say idle, we'll just say, we'll say below 900 RPM, this spring isn't strong enough to overcome centrifugal force, or this centrifugal force most of the time is pushing it at centrifugal force. There we go. I'm explaining this weirdly. Centrifugal force at high RPMs pulls the weight of this pin in. But if we go slow enough, centrifugal force isn't strong enough anymore, and the pin gets pushed in to the propeller. Now, if we did anything like shut the engine off, and the feathering spring and the compressed gas charge tried to push the pitch actuator down, the propeller couldn't change pitch because the pin is stuck in here. So the blade stays at low pitch. When we start the engine back up, and we get the engine up above, say, 900 RPM, then centrifugal force will push on this metal pin enough to counteract the spring, and it's not in the propeller hub anymore. Now the propeller can change pitch all at once. So you're going to see on airplanes, the vast majority of them with counterweights, that the propeller stays in low pitch because we have a nice spring-loaded latch pin to keep it in low pitch when we shut the engine down. Reverse pitch, I already told you. Turboprop, there's very, very few piston engines. You might be able to find a DC4, some 1950s big radial engine, but we're going to say for effective purposes only turboprops have reverse pitch on them, and that's of course really, really low pitch. Hey, you're going to go pre-flight the aircraft, and now you're pre-flighting the propeller. Unlike a fixed pitch prop that no oil is going to, now we have a propeller that oil gets pumped to, so we're going to look for oil leaks. If we had oil coming out of the propeller, that would be bad. We're going to have to ride it up, and the airplane's not going to get flown that day. If we have an airplane with hot props or with alcohol props and there's rubber boots glued to it, we're going to check the rubber boots for condition, and we're going to try to look for electrical contacts if they're electrically heated propeller to make sure the contacts are all right. Generally speaking, you're going to generally read, hey, don't pull on the propeller blades. If it's a fixed pitch blade, you could probably get away with, but only if you pulled on it right next to the hub. For instance, here's the spinner, here's the propeller, and if you grabbed on with your fingers right here and pulled, and grabbed on your fingers right here and pulled, and didn't pull too bad on a fixed pitch propeller, you're going to be okay. However, standing operating procedure, if it says don't do that, don't do it. Cycle propellers, and we're talking about constant speed props with a prop lever. There's two reasons why before takeoff. We're going to cycle it before takeoff when we're doing an engine run up. Reason number one, we're going to check prop and governor operation to see if it's working correctly, and two, we're going to get hot, thin oil into the propeller hub at the actuator so that it works rapidly. If the oil is thick, because it's cold, it won't go into or out of the propeller very easily, so the propeller won't change pitch very rapidly. So we don't want to overspeed the engine on takeoff by pushing the throttle forward, and the propeller blade won't go to a high pitch to keep the RPMs the same. To keep them constant right at redline, the engine RPM redline might go too high. So to preclude that, to keep that from happening, we're going to cycle that prop a couple of times, but we're doing it anyway just to make sure the propeller and the governor works anyway. So now if it's hot and thin oil, that'll allow the oil to go to and from the pitch actuator very easily, and the blade will change pitch rapidly. And of course, for in-flight, we've been along, let's just say we're at minus 40 degrees Celsius, which by the way happens to be minus 40 degrees Fahrenheit, because we're flying over the northern United States in the middle of winter, and we'll say we're at 24,000 feet. We'll say we're flying a pressurized piston twin, and we've been flying along at the same speed, all at the same power setting, so we haven't been pumping oil to the propeller, and we haven't been pumping oil out of the propeller because we're in an on-speed condition. So out there in that propeller hub, that oil, it's going to get cold. It's going to get really stinking cold. So now if we're flying along and then all of a sudden we dive the airplane a little bit, we just use trim, we don't pull back on the throttle, then the propeller, the oil can't go into or out of the propeller very easily, and it's not going to change pitch. It's just like going downhill. If you don't change, if you leave your foot at the same spot, the engine RPMs are going to go too high. So it might be that what we want to do is cycle the propeller, not very much, just say 50 RPM. We might just want to grab one propeller lever and pull it aft just to get a 50 RPM reduction and push it forward and pull it back and push it forward 2 or 3 times. And if we're in a twin, we do that on the other prop lever, and that allows hot oil to get in and come back out, hot oil to go in and come back out. So now the oil in here is hot and thin, and we can again have rapid pitch actuation change so we don't accidentally overspeed the engine in a descent. You know about the connections. Any questions, any improvements, you know how to get a hold of me. Thank you very much.